Packet captures Kali Linux. Armin Shahriarian. Packet captures. As you are performing network testing, you will find it useful to be able to see what is being transmitted over the network. To see what is sent, we need to use a program that captures packets. In fairness, though, what we are doing is capturing frames. The reason I say that is each layer of the network stack has a different term for the bundle of data that includes that layer. Keep in mind that headers are tacked on as we move down the network stack, so the last set of headers added is the layer 2 headers. The protocol data unit, PDU, at that layer is the frame. When we get up to layer 3, we are talking about a packet. Layer 4 has datagrams or segments, depending on the protocol used there. Years ago, capturing packets was an expensive proposition, because it required a SPE chain network interface that could be put into promiscuous mode. The reason it's called that is because by default, network interfaces look at the MAC address. The network interface knows its own address because it is attached to the hardware. If the address of an inbound frame matches the MAC address, the frame is forwarded up to the operating system. Similarly, if the MAC address is the broadcast address, the frame is forwarded up. In promiscuous mode, all comers are welcome. This means that all frames, whether they are addressed for this particular system or not, are forwarded up to the operating system. Being able to look at only frames addressed to that interface is nice and valuable, but it's far more valuable to be able to see all frames that come across a network interface. Modern network interfaces typically support not only things like full duplex and auto-negotiation but also promiscuous mode. This means we don't need protocol analyzers anymore, as the hardware that could do this work was often called, because every system is capable of being a protocol analyzer. All we need is to know how to grab the frames and then peer into them to see what is going on. Using dump. While other operating systems have had other packet capture programs, like Solaris had Snoop, the de facto packet capture program these days, especially on Linux SYS TEMS, is dump if all you have is access to a command line. We will take a look at a GUI a little later, but there is a lot of value in learning about dump. You won't always have access to a full desktop with a GUI. In many cases, you will have only a console or just an SSH session that you can use to run command line programs. As a result, dump will become a good friend. As an example, I used it earlier to verify that the protocol being used by our SIP testing program was really just using UDP and not using TCP. It has a lot of value in understanding what is going on with a program that isn't otherwise telling you. Before we start looking at options, let's take a look at the output from dump. Being able to read what is happening by looking at the output takes some getting used to. When we run dump without any options, we get a short summary of the packets that are passing through. Example 2 to 10 is a sample of dump output. Example 2 to 10. Dump output. The first column in the output in example 2 to 9 is the timestamp. This is not anything that has been determined from the packet itself, since time is not transmitted as part of any of the headers. What we get is the time as the hours, minutes, seconds, and fractions of seconds after midnight. In other words, it's the time of day down to a fraction of a second. The second field is the transport protocol. We don't get the layer 2 protocol because it's determined by the network interface, so it goes without saying. In order to know the layer 2 protocol, you need to know something about your network interface. Commonly, the layer 2 protocol will be Ethernet. The next set of data is the 2 endpoints of the conversation. This includes not only the IP addresses but also the port information. So, Binkley.LAN is the source of the first packet, and TestWe.Here is the destination. Without telling it not to, dump will convert IP addresses to host names. To disable that function, you would need to provide an N on the command line. This would speed up your capture and lower the number of packets captured, since your system won't be doing a DNS lookup for every frame that comes by. You will notice that along with each IP address is another value from our source address, Binkley.LAN.57137, the 57137 is a port number. This is the source port, and on the receiving side, you can see testwe.here.domain. This means that testwe.here is receiving a message on the port used by domain name servers. Again, just as in the host name versus IP address, if you don't want dump to do a lookup on the port number, based on well-known port numbers, you can add N to the command line. And dump will just present you numeric information. In this case .domain translates to 0.53, which is the numeric value. We know that this is a UDP message because it tells us after the destination information. Primarily, what you see in example 2 to 10 are DNS requests and responses. This is a result of having dump doing reverse DNS lookups to determine the host name associated with the IP address. The remainder of each line from dump output is a description of the packet. In the case of a TCP message, you may see the flags that are set in the TCP header, or you may see sequence number information. This time, we'll take a look at more verbose output by using the V flag. Dump sup ports multiple V flags, depending on the level of verbosity you are looking for. We'll also take a look at using the N flag to see what it looks like without any address lookup. Example 2 to 11 shows the more verbose output. Example 2 to 11. Verbose output for dump. The output looks largely the same except that this is all numbers with no host names or port names. This is a result of using the N flag when running dump. You will still see the 2 endpoints of each conversation identified by IP address and port number. What you get with V is more details from the headers. You will see that checksums are verified as correct or incorrect. You will also see other fields including the time to live value and the IP identification value. Even if we switch to VVV for the most verbosity, you aren't going to get a complete packet decode for analysis. We can, though, use dump to capture packets and write them out to a file. What we need to talk about is the snap length. This is the snapshot length, or the amount of each packet that is captured in bytes. By default, dump grabs 262,144 bytes. You may be able to set that value lower. Setting the value to 0 says that dump should grab the maximum size. In effect, this tells dump to set the snap length to the default value of 262,144. To write the packet capture out, we need to use the W flag and specify a file. Once we've done that, we have a packet capture (PCAP) file that we can import into any tool that will read these files. We'll take a look at one of those tools a little later. Berkeley Packet Filters. Another important feature of dump, which will serve us well shortly, is the Berkeley Packet Filter, BPF. This set of fields and parameters allows us to limit the packets that we are grabbing. On a busy network, grabbing packets can result in a lot of data on your disk in a short period of time. If you have an idea of what you are looking for ahead of time, you can create a filter to capture only what you are going to be looking at. This can also make it quite a bit easier to visually parse through what you have captured, saving you a lot of time. A basic filter is to specify which protocol you want to capture. As an example, I could choose to capture only TCP or UDP packets. I might also say I want to capture only IP or other protocols. In example 2 to 12, you can see a capture of ICMP-only packets. You will notice that in order to apply a filter, I just put it on the end of the command line. What results is the display of only ICMP packets. Everything still comes into the interface and is sent up to dump, but it then determines what to display or write out to a file, if that's what you are doing. Example 2 to 12. Dump using BPF. Root at rosebud #dump ICMP. One thing I can do with these filters is use Boolean logic. I can use logic operators to be able to develop complex filters. Let's say, for instance, that I want to capture web traffic. One way I could do that would be to say TCP and port 80, I am grabbing all TCP packets that have the port as 80. You'll notice that I don't mention source or destination with respect to the port number. I certainly can. I could use SRC port 80 or DST port 80. However, if I don't specify source or destination, I get both ends of the conversation. When a message goes out with port 80 as its destination, when the receiving system replies, the port numbers get swapped. Port 80 on the response becomes the source port. If I were to capture only SRC port 80, I wouldn't get any of the messages in the other direction. This may be exactly what you are looking for, of course. But it's something to keep in mind. You may find that you need to indicate a range of ports to be grabbed. You could use the port range primitive to capture a range of ports, like 80 to 88, for example. The language used for BPF provides a lot of capability. If you need really complex filters, you can certainly look up the syntax for BPF and examples that may provide you something specific that you are looking for. What I have often found is that specifying the port is valuable. Also, I often know the host I want to capture traffic from. In that case, I would use host 192.168.86.35 to grab only traffic with that IP address. Again, I have not specified either source or destination for the address. I could by specifying src host or dst host. If I don't indicate, I get both directions of the conversation. Developing even a simple understanding of BPF will help you focus what you are looking at down to data that is relevant. When we start looking at packet captures, you will see how complex a job it can be to do packet analysis because there are just so many frames that contain a lot of detail to look over. Wireshark. When you have your packet capture file, you will probably want to do some analysis. One of the best tools for that is Wireshark. Of course, Wireshark can also capture packets itself and generate PCAP files if you want to store the capture for later analysis, or for analysis by someone else. The major advantage to Wireshark, though, is providing a way to really dig deep into the contents of the packet, rather than spending time walking through what Wireshark looks like or how we can use Wireshark for capturing packets. Let's jump into breaking apart a packet using Wireshark. Figure 2-4 shows the IP and TCP headers from an HTTP packet. Figure 2-4 header ELDs in Wireshark. You can see from just this image that Wireshark provides far more details than we were getting from dump. This is one area where GUIs have a significant advantage. There is just more room here and a better way to present the amount of data in each of these headers. Each field in the header is presented on its own line so it's clear what is happening. You'll also see here that some of the fields can be broken out even more. The flags field, for example, can be broken open to see the details. This is because the flags field is really a series of bits, so if you want, you can open that field by clicking the arrow, or triangle, and you will be able to see the value of each of the bits. Of course, you can also see what is set just by looking at the line we have presented by Wireshark because it has done the work for us. For this frame, the don't fragment bit is set. Another advantage to using a tool like Wireshark is that we can more easily get to the contents of the packet by finding a frame that we are interested in because it's part of a conversation that we think has some value. We just need to select Follow TCP Stream. What we will get, in addition to only the frames that are part of that conversation, is a window showing the ASCII decode of the payloads from all of the frames. You can see this in Figure 2-5. Wireshark also color codes the output. Red is the CLI end messages, and blue is the server messages. You will also get a brief summary at the bottom of the window indicating how much of the conversation was the client's end, how much was the server's. Figure 2-5. Follow TCP stream output. Wireshark has the same filtering capabilities that we had with dump. In the case of Wireshark, we can apply the filter as a capture filter, meaning we will capture only packets that match the filter, or we can apply the filter as a display filter to be applied to packets already captured. Wireshark will provide a lot of help when it comes to filtering. When you start typing in the filter box at the top of the screen, Wireshark will start trying to autocomplete. It will also indicate whether you have a valid filter by color coding the box red when you have an invalid filter, and green when it's valid. Wireshark has the ability to get to about every field or property of the protocols it knows about. As an example, we could filter on the type of HTTP response code that was seen. This may be valuable if you generated an error and you want to look at the conversation that led to the error. Wireshark will also do a lot of analysis for us. As an example, when we were fragmenting packets earlier using FragRoot, Wireshark would have colored frames that weren't right. If a packet's checksum didn't match, for instance, the frames belonging to that packet would have been colored black. Any error in the protocol where the packet is malformed would result in a frame that was colored red. Similarly, TCP resets will get a frame colored red. A warning would be colored yellow and may result from an application generating an unusual error code. You may also see yellow if there are connection problems. If you want to save a little time, you can use the Analyze menu and select Expert Info to see the entire list of frames that have been flagged. You can see a sample of this view in Figure 2-6. Wireshark has so many capabilities, we aren't even skimming the surface of what it can do. A lot of what you may find it useful for is just to see the headers for each protocol broken out in a way that you can easily read them. This will help you see what is happening if you run into issues with your testing. One other feature I should mention is the statistics menu. Wireshark will provide graphs and different views of the data you have captured. One such view is the protocol hierarchy, as you can see in Figure 2-7. Figure 2-7. Protocol hierarchy in Wireshark. The protocol hierarchy view is good for, among other things, quickly identifying protocols that you don't recognize. It also helps you to determine which protocols are the most used. If you believe, for instance, that you are using a lot of UDP-based attacks, but UDP is a small fraction of the total number of messages sent, you may want to do some further investigation. Wireshark comes installed out of the box, so to speak, with Kali Linux. However, it can also be installed on other operating systems such as Windows and Mac OS as well as other Linux distributions. I can't emphasize enough the value of this particular tool and the amount of work it can save after you get the hang of using it. Being able to completely decode application layer protocols so it can give you a little summary of